Hi everyone, my name is Brooke and I'm a geologist. In this video I've collected together some of the highlights from my TikToks to show you what I'm doing over there. If you want to see more geology based action, then follow me on there because I post a couple of times a day and you get to see what I'm doing as I'm doing it. In these videos I'm going to show you some of the fossils and microbial textures I've been finding some of the fossils and microbial textures I've been finding in the 1.4 billion year old mudstones that I study from Northern Australia. I hope you enjoy looking at these tiny little microbial fossils as much as I like finding them. Just organising my Australian samples and I found a really weird rock that was cool and I wanted to share it with you. I remember picking it out of the core tray years ago and thinking, that's weird, I'll get around to figuring it out, and then I never did. Still don't know what's going on with it, but let's have a look. Here's what it looks like. Let's have a look at it under the microscope. So the bar at the top is in millimeters. Okay, no idea what's going on. What I can tell you though is everything in this is really soft, softer than steel, softer than your fingernails. The green stuff, which makes up most of the sample, this stuff here, is a mixture of berthurine and kaolinite, iron smectite, and then some detrital stuff, like some quartz silt grains and some muscovite, detrital muscovite grains. So this green stuff was mostly precipitating on the seafloor, I guess, or lake bed or whatever it was. I'm not sure what these red things are though. They're very soft as well, and they're kind of microcrystalline. They're definitely part of the sediment because you can see that the rock warps around them. Well, you'd be able to see if it was in focus, but it's not. So maybe they're oxidized framboids because it is really super soft stuff. But it's crystalline in a way that secondary oxides usually aren't. Who knows? I'll have to go back and check the XRD data and maybe try and have a look at it under a microscope by making a thin section. Anyway, I just wanted to share that cool rock with you. This one's about 1 billion, between 900 million and 1 billion years old, so pretty young compared to what I usually work with. There's potatoes. This is a moment of discovery. This tiny little black bean-shaped thing is a 1.4 billion year old fossil of some kind of eukaryotic organism. I spent hours looking over these bits of shale just to find this one little critter, and it's super tiny. Oh, no. This is hard. So this is how small it is compared to the end of my tweezers. Oh, so tiny. And that's how big my tweezer is in real life. You can't even see the fossil really on the shale. So now I've found it under the microscope. What I need to do is mark it with this wee bit of chalk so I can find it again, and then I'll make a note on my spreadsheet. Sample worth looking at and going through the trouble of making a microscope slide and digesting it in the acid to try and extract the fossil out so we can look at it closer. Really exciting. Oh my gosh. I've painstakingly marked that out with chalk so I can find it again. And we can see under the microscope just what that chalk looks like. Oh well, maybe we can't. I need a better holder for this. I need to get a proper mount so we can use my phone down the microscope. Yeah, there's the fossil and there's the chalk. So I'll be able to find that again. How exciting. For me, it's immensely exciting. Can't wait to see what it looks like once I've extracted it and have it on a proper microscope and then an electron microscope. But I've still got a lot more rocks to look at. I think 600 and something samples in total. So I best get cracking. There's potatoes. This rock is a piece of 1.4 billion year old seafloor. The arrow there points upwards So if we went back to Australia 1.4 billion years ago, this would have been the seabed. This white area is chalk that I've used to mark out something interesting I want to look at later. If you look very carefully, and if we get the angle righting against the light, you'll see that there's lots of little crisscrossing patterns, little trails, little wrinkles preserved in the mud. And those wrinkles and trails are the remains of microbial mats of bacteria, and then the early ancestors of eukaryote, what would go on to be modern eukaryotes like algae, living on mats stuck to the seabed, getting pushed and pulled by the currents and leaving impressions on the ancient seafloor. For me, this is really incredible. We're seeing the movement of water and of life of these microbes that were sat on the seafloor in the slimy mud, wafting backwards and forwards and being pulled around and leaving traces across a gap of over 1 billion years. And that's absolutely incredible. Normally when you see things like bones and fossils, it's a kind of abstract, like you don't know how long the creature was dead before it got fossilized. This is like getting a glimpse of a moment in time from over 1 billion years ago. When you think about it, the past is further away than the most distant star. One day we'll be able to travel to other planets. We've already been to the moon, we can send robots to planets in our solar system, and eventually we'll go to other planets in our solar system and other planets around other stars, but we can never go back in time. So this is like really incredible, being able to see the movement of water and the impressions left by life in real time as it was made on the sea floor of a sea that no longer exists over 1 billion years ago. And I was the first human to ever see that, and as you watch it, you'll be the first humans to ever see this. Absolutely incredible. And people wonder why I like rocks so much, right? Liz potatoes. Hi everyone, my name is Brooke and I'm a geologist. I'm back here in the office at the University of Liège, where I'm looking at some more of the 1.4 billion year old Australian mudstones that I've been studying, that were collected from drill core from the northern Australian desert. And I've got some more of these beautiful microbial structures here, but from a different section from the same drill core. So let's have a look at them. So we've got one bit of drill core here, and it went together like this. I drew the arrows on it to see, so we know which way is up, as I collected it from the sampling bay. And it's split here along this bedding plane, because we've got these dark and light patches. The light patches are sand and the dark patches are mud. And we can see it on the surface here, which was originally the seabed, all those billions of years ago. We've got all of these lovely textures. So we've got these microbial textures, and you can see here where things are getting pressed into the mud. And we've got some sedimentary textures where we were having the sediment getting pushed around by currents, but something was holding it in place, and that's usually the glue that microbes make their little mats out of, and that's what sticks the mud together. But if we look on this side, this is the underside now, the bottom of the overlying layer. So the arrows are pointing down now. We can see we've got all of the impressions still from where the microbial filaments and the threads and blobs were pressing down. So this is the holes where they were pressing down, and this is the actual mud-filled cavities that filled in the actual mat itself. Well, it didn't fill it in, more like the mud grew within it, because the mats control the chemistry. If you look closely, you can see that there's these thread shapes all crisscrossing over each other, and these filaments are often made by photosynthetic bacteria. So I've zoomed in with a microscope now, and we're looking at the sediment surface again, and here's those filament impressions along there and there on there in our microbial mat. They're difficult to see because they're so subtle, but if I rotate them you can just about make them out. There's all of those other blobs where the microbes were holding the sediment together while the water currents were moving it around. So let's go over here and have a look at the upper part of the bedding surface, and then you can see those microbial filaments that have been filled in with the mud much more clearly there. And there you can see how they're all crossing over each other. And that's something you wouldn't really get if it was just a sedimentary structure made by the currents pushing it about on its own. So that's one of the reasons we know, ways we can tell that it was biology doing this as opposed to just abiotic processes. There we go, we can see there's a nice one there. So the next step will be to dissolve this in acid to extract the fossils, and then to slice the rock up really thin and have a look at that using a petrographic microscope. So that'll be in a future video. Laters. So it takes a while to do the acid digestion, which process we call maceration, and it takes a while to make the thin sections and study them. So I'll have to do that in a future video in a few weeks or so. But I've got some I've already prepared, and we can have that from a different drill core of the same age and the same unit of rocks, so we can have a look at them in a couple of videos time. There's potatoes. You need to be really careful when you're looking for fossils in rocks this old. Even when you do find really well preserved rocks like we have, like these 1.4 billion year old shales, there can be lots of things that look like fossils that aren't actually fossils, and I just got fooled by one now and got really excited until I realised it was actually not a fossil. So here's the sample, some of our black shale from a depth in the core of 1,272 metres below the surface, and you can see it's very black and the oil is already decaying out of it in the few years since it's been extracted. Oxygen in the atmosphere are reacting with the sulfides to create sulfates, and also modern bacteria are eating the carbon and the phosphorus and the other material that's in there. But let's have a look at it under the microscope. So you've probably already spotted all of these beautiful fern-like dendritic structures. Sometimes you do get branching microbes in this kind of material that looks like that, and this would be really exciting. But I double checked myself before I double wrecked myself. And if we look on the side, we can see that we've got, if we turn the sample on its side though, we can see, yep, we've got all of these beautiful dendritic structures, and we wouldn't expect them to be growing along the side. We'd expect them to be growing flat along the bedding planes, and you can see that these are quite clearly crystals of some kind. So these are probably more sulfate crystals or evaporite salts that are growing out of the sample because it's getting oxidized and consumed by modern bacteria. Either way, it's really cool, and it's nice to see that even stuff this old is getting recycled back into the Earth system. So that nearly fooled me, and I've been doing this for a long time, so it's easy to see how other people can get fooled. Right, there's potatoes. Everyone, well, after the fossil arm of those weird crystals, we're now down at a depth of 1,326 metres underground and found some actual fossils that you can kind of see with the naked eye. Not just the impressions in the mud, but the actual organic cells themselves, although they're being turned to carbon. Let's have a look. Okay, So if you look on the bedding surface here, all these black bits are our organic matter, and you see this one here, that kind of bean-shaped boyo, that's one of our fossils. And once you look closely, you'll see they're all around the same size, so this is the biggest, and they're all bean-shaped. So this could be the fossil of a large single-celled algae called Tuuria that's been found in rocks slightly younger than this all over the world. So there's our little pal on the bedding surface. Let's zoom in. See what details we can see. Yeah, not an awful lot, but still pretty good considering how old it is. So if you're struggling to see it, our fossil is here. And some Tuurias can be up to a few centimetres long, but most are around this size. And it doesn't show up well on the camera, but there's actually loads of them, but much smaller, all those little dark patches. And the fact that they're made of organic carbon, the fact that they're within the sediment rather than on top of it, and we know that because we can see here we've got clay flakes overgrowing it, and because they've got a very tight constrained size range, we can say that yeah, this is probably biological and it's a fossil. And then also the fact that people have found lots of these all over. So there we go, that was pretty cool. So what we can do now with this bit, because I can see from the side that there's lots of those little Tuurias and other organic fossils within that rock, is I can send it away to get sliced up to make thin sections so I can look at it under the petrographic microscope even closer, and then I can take it to the lab to get, in a few weeks, to get dissolved, and so we can extract those fossils and look at them close up, free of the sediment. So that's going to be really cool. There's potatoes. Looking at one of my 1.4 billion year old samples again, and this is a piece of drill core I've cut in half so we can see what's inside. So this is the top here where my tweezers are, and this is the surface of one of the microbial mats, and inside we can see all these fine laminations full of organic matter. I've put water on it as well so you can see the details better because it hasn't been polished yet. All these little wiggly laminations are organic matter, and that's where we'll find the fossils when we slice this up and put it on a petrographic microscope, and then when we extract the fossils with acid. And you see we've got this lighter coloured material here where the mat is. This is the dark mud the mat was sat on here. But this lighter material is a mixture of sand grains that were getting stuck in the mat, and then clay, green iron-rich clay that's growing inside the mat, because the microbes were able to change the chemical composition of the water in the mat to suit themselves. So this is maybe a centimetre to half a centimetre maybe thick, and it's lost about 80% of its volume due to the rock and mud getting squished during preservation. So this would have been 80% thicker, and when you find these things in the modern day in real life, they're like big squidgy masses, kind of like lasagna that's green and red and purple and has all kinds of different communities of bacteria and microbes living in it. They're really, really cool. Okay, it's drying out now, so we're losing the detail. So next time we'll have a look at this on the petrographic microscope so we can see if there's any tiny little cells in it, and to try and identify what minerals are growing in there. Okay, there's potatoes.